Okay, the next topic that I want to show you a little bit of is a concept involving general relativity, which is there's a concept of putting an elevator out in space. This is like, it maybe shouldn't even be called an elevator, but should be maybe called a rocket ship, like a room inside of a rocket ship. And you can imagine as the rocket is coming down, its retro rockets are firing so that it comes to a complete stop and then accelerates upward over time. And what's going on here is during that time, little balls are being thrown at the ceiling at a constant frequency and a constant rate. But the constant rate is determined not by the speed of the elevator, but from here the speed outside the elevator. And what you see as the elevator increases in speed, these balls inside the elevator slow down. The frequency stays the same, but they get closer together because they are slowing down. Okay, now here is a space-time diagram of the same situation. As time goes by, you can see whatever the objects are released from the bottom of the elevator at the same rate. Okay, you can see that here, I could just enter times in there. I've got a start time at -8 and a release rate of 0.5, so it should be every 0.5 seconds. So you can see a photon is released at -6.5, -6, and -5.5, etc. So these release rates, as it's being released from the bottom of the elevator, is quite consistent. But if you look over here at t equals like 2.5, say, you'll notice that the photons start to get bunched up. So right here there's 3 of them in view in the elevator all at the same time. And here at time equals 5, it gets quite drastic with 1, 2, 3, 4, 5 photons, or well, objects in the elevator at the same time. Notice part of the idea of this is a little bit strange because we're requiring whoever is inside the elevator to be throwing the ball up throwing the thing up towards the top of the elevator with a speed that is based on the outside reference frame. And then once they are released, they move at a constant velocity with respect to that outside reference frame. Now from inside the elevator, it's really hard to see it here, but well, towards the end of this you can kind of tell. But watch, let me slow that down a little bit and play it. You can see the balls are actually slowing down as they rise. So if the elevator continued to accelerate past the speed of the ball, then they would start to fall. So this is kind of a hybrid, imagining first of all that the elevator is not in a gravitational field. So that means all motion of the ball is completely linear, but the person who's throwing the ball upward, or throwing the ball forward in the accelerating elevator, is throwing that ball with a constant velocity relative to some outside observer. So what we're going to do is try to contrast that with what happens if the acceleration of the elevator is such that there's a significant acceleration compared to the speed of light over that period of time. And instead of a ball being thrown at constant velocity relative to some outside observer, we want the speed, we want the to be a photon moving at the speed of light, which would also be constant relative to some outside observer. So the one big change is that instead of being two parabolas, this parabola would be represented by x equals 1/2 at squared, and this other parabola would be x, let's say, equals 1/2 at squared plus the height of the elevator. Now I've got another piece of code here, and I think this may be the hyperbolic forms of the elevator floor and elevator ceiling. But let's test that out to see what we can find. This would be y minus y sub naught. Well, first of all, let's just write it as, I'll just change this to y, and I'll start with this one, I guess. Y equals that. So if I add y sub naught to both sides, I would have y plus y sub naught equals square root of y sub naught plus ct squared. Now I'm going to square both sides, so I will have y plus y sub naught squared equals y sub naught plus ct squared, and then I'm going to subtract ct squared, so I will have y minus y sub naught squared minus ct squared equals y sub naught. And what are we looking for? We're looking for an equation for a hyperbola, which is generally of the form x squared minus y squared equals something else squared, some hyperbolic radius. So in particular, this x squared minus y squared equals r squared would give us a hyperbola that essentially look like this and this, with this distance here being r, where this side is x and this side is the y-axis. And so what this equation does is it just kind of moves it over. You could also graph this with x being on top and y being on the side, and getting a graph that goes like this. And so if you have that, and then you have this radius, is that the proper radius? I see what I did. I left out a squared right here. Y sub naught squared here, y sub naught squared here, and this should be y sub naught squared here. And last thing I did was I changed that minus to a plus. Okay, that's good, because that will basically take this hyperbola, pair of hyperbolas, and it shifts it down to this. Well, so that basically this direction here is 2 y sub naught between those. It's 2 times that hyperbolic radius. And the other thing is, since I kind of got rid of a solution here, but because this is the positive square root, we can eliminate that lower side, and we just have this top side of the hyperbola. So let me ask another question while I'm thinking of it. This seems to be another equation for acceleration. We're more familiar with the equation y equals 1/2 at squared, but we seem to have come up with another form of an equation for acceleration, which is relativistic. Y equals the square root of y sub naught plus ct squared minus y sub naught. However, we seem to have lost something here. in this form, we have an acceleration which is in meters per second squared, for instance. In this one, we have what appears to be some kind of radius of a hyperbola. Now, the information contained in the two forms is the same. I remember I don't recall exactly how to do the calculation right now, but I do remember that the Earth's 9.8 meters per second squared was approximately equal to a hyperbolic the curvature of the parabola generated by 1/2 at squared is approximately the same as the curvature of a hyperbolic radius with a curvature with a hyperbolic radius of y sub naught equals 1 light year, if I remember correctly. I'd have to check that. I'll probably have to leave that for later, but it does suggest another improvement to this particular equation. I do believe that the actual comparison to the speed of light never really came up in the original when I was working on this before. It is should probably be c squared t squared, which would make pretty much everything look a little bit more reasonable, because otherwise the units won't come out right. I think it really didn't matter when I put it into the code here, because c was set equal to 1 anyway, so 1 squared is 1, so it didn't make any difference that mistake was made. Anyway, I think I'll wrap it up here. I hope to show you in the next video what happens when those hyperbolic radii are plugged into the equation.